Hey, well, good afternoon, everyone. Thank you for attending today's webinar on residential roof assemblies. This webinar will be recorded and it's posted to the Code Adoption Toolkit on Colorado Energy Office's YouTube page. If there are any issues with audio, please feel free to write me in the chat. My name is Erica DeLello. I'm a Senior Project Manager for Noresco. And today's training materials were created by Samskoda Associates with the training being sponsored by the Colorado Energy Office. So on the next slide, we've got all the training types that we offer, including the webinar series. This is the last within this series. Hopefully we'll be adding more, but stay tuned and check out your email for more information. We do also offer role-based trainings, which is basically taking a look at the energy code through the eyes of the user. So if you're a building inspector, if you're a plans examiner, if you're a designer or contractor, we have deep dive walkthrough training specific to your role. So if you're interested in any of those, or if you're interested in a specific topic, feel free to reach out to me. We also offer technical assistance for code adoption. So if your jurisdiction is looking to move forward with the latest I-codes, we offer free technical assistance and are able to help in a variety of different ways. Okay, so most of you know about the Code Adoption Toolkit. However, my favorite part of one of the resources that we've created is the Colorado Codes Helpline. You can submit a question on any of the I codes or reach codes in the state of Colorado. So for example, if you're a jurisdiction and need assistance on a plan review, or if you're a homeowner or engineer and have a question about code applicability, you can submit a ticket and subject matter expert, will get back to you in just a couple days' time. So you can access this helpline through the QR code, and it's also linked on the Code Adoption Toolkit. Throughout the webinar, we do want to encourage questions, but I'm going to hold the questions to the end so that we can get through all of the content. If you do have questions, feel free to raise your hand as well at the end, and you can speak directly to our presenter today. And our presenter today is Andre Hyen. And I will go ahead and stop sharing my screen and let you take it from here, Andre. Oh, and one last thing, there is a survey or a poll. If you could please take a minute to fill that out, as well as the post-training survey at the end. That helps us to improve on these webinars. Thanks.
All right. Thank you very much, Erica. I'm really excited to be here and be able to share with you guys today. Speaking of sharing, let me get my screen up and running here. Is that coming through?
Yes.
All right. Well, thank you very much for joining me, everybody. I hope you're going to enjoy your lunch today and be able to talk about some energy code related fun as it relates to residential roof assemblies. These are a pretty unique part of what we look at as code officials, especially with all the change that sort of occurred. Residential roofs have gone from typical gable designs in the 70s, 80s, a lot of ranch style houses that are really common in the some of the metro areas here in Colorado, to much more complex designs to accommodate a number of different consumer preferences, installation styles, right? Things like that. And so we're going to kind of break that down as we go ahead and move along. So to give you guys just a rough agenda of what your next hour is going to look like here, we're going to talk about the role of roofs in construction, what materials are used, especially for some of those folks, because I'm really big on trainings like this where we meet everybody where they're at. Some folks have a lot of speciality in energy code related stuff, and I could talk to them about the most technical aspects of that, but it doesn't necessarily always translate to some of the other nomenclature and things that we'll have for other parts of design or other parts of installation. So we're just going to start from kind of ground up. How do roofs work? What's included in them? We're going to talk about the science behind this. We're going to go over heat, ventilation, moisture, thermal conductance, a number of the components that we look at to designing the thermal envelope and how it's going to relate to residential roof assemblies. Then we'll crack into the actual thermal envelope itself. how it relates to depiction, some of the specific code sections you have, and especially how we deal with ventilation. That's going to be a major component of what we discuss today because it determines a lot of then how we go about using the right materials, right methods in that attic space and in that thermal envelope. And then we're going to end on some special considerations from Colorado for Colorado, especially given that the Wildland Urban Interface Code Board has Wildfire Resiliency Code Board actually specifically for that piece of statute, but how they have made some recommendations for adoptions and how some of the folks in some of these wildfire prone areas have been handling this, which was actually some of my experience from my previous jurisdiction before I came over here to Shumscoda. So hopefully I can share a little bit about that and how those kind of are going to work together and maybe change things from either a design perspective or some of the best practices that you might see in the field related to roofs. So with that, Erica's exactly right. If you have any questions, please put them in the chat, and can't wait to get to them to get through any of your interests. Basically, this is your time, and I want to make sure that it's used effectively for you. So the role of roofs, right? We use them as shelter from the environment, right? If we had to describe a house to a child, it would be four walls and a roof. That's typically our starting off point from this. It's one of the most important places to be able to insulate properly. That little quote you see from the Better Buildings section of US DOE gives some reference to being 33% of the building energy losses in a home. And it's dependent on the climate zone that it's in, some other stuff there. But I mean, a third of the the money that you spend warming things in your furnace, right, in order to be able to warm your home, to see that being such a contributory force towards the losses and the dollars spent heating a home makes it a prime target for improvement. And we've seen that through different code cycles. Through the 18 we saw sort of a crest in total insulation value being attributed to the roof in the 21, and then in the 24 code we're going to look at how it's gone back to a bit lesser in terms of insulation because of some concerns on payback and things like that. But ultimately, it's pretty clear that it's been targeted as a very important part of the discussion when it comes to energy efficiency and the design of the thermal envelope. It's also a membrane that we have to think about, right? It's in flux. It's getting pulled on by wind. It's getting pulled on by shear forces within the home, and shear forces, transmuting its way up through that attic. It's also a membrane that's being penetrated very often. So that is your plumbing pipes and vents. That can be solar PV. It can be chimneys. It can be ductwork and B venting specifically, right? Exhaust ductwork. It's a number of different things that pass through these assemblies. And then we also have desired penetrations as well, like skylights. And so this is a place where not only is it common that we want to insulate it well, and it's a key part of our thermal envelope, but it's a place we put a lot of holes in. There's just no getting around it. And then it typically will also need its own ventilation depending on the type of thermal envelope and the way that you've gone ahead and insulated that roof system. It's also one of the places that's the most replaced place on a home, especially here in Colorado where we're in Hale Alley, right? So, a lot of houses in the metro area see roof replacements on a very regular basis. That can be for, hail damage, that can be for a number of different things. I see a comment here from Brian. It's been my experience that most environments, attic ventilation is crucial, but in Colorado, it's just a way of allowing snow and moisture into the roof assembly. It actually defeats the purpose of ventilation. Brian, you were spot on. We're going to talk about how some of the tactics used previously for ventilation, some of the misunderstanding about how to install ventilation properly has definitely been a contributory factor towards that. I can definitely agree with you that I have been in my fair share of like attic spaces, for instance, where I have seen like gable end vents that have become sort of intrusion areas for water to get into the rest of the assembly there. And then there's also no doubting it as well. We've seen the effects of poor ventilation on the other side of that, where there's not enough. And then you see premature shingle failures. Colorado's definitely been a place where you can highlight a lot of those, where you get these brittle asphalt shingles and things because of a lack of ventilation, because of the wrong science basically being used and the wrong affect to be able to put this whole thing together. So great point, and we will kind of consider that as we move along. But you're spot on that there is a right way and a whole lot of wrong ways to go about doing this. So what are the components of a roof, right? Well, typically, right, on most residential homes, we're talking about OSB decking over a structure to act as a nailable substrate. After that, we usually have underlayment of some type. But this also can depend on the type of roof that we're putting on. We'll talk a little bit about this. I'm not going to get into too much detail, but there are certain roof types, like say wood cedar shake, for instance, which is still allowed in large swaths of Colorado, sometimes even preferred by certain HOAs, and it's a requirement to use a roof type like that or something with a similar architectural feature. And in those areas, those roofs definitely were designed in such a way as they had significantly more breathing than what we see on a OSB and otherwise completely felted in roof. These were done with multiple layers of woven in felt over typically a space decking. Or spaced sheathing method. So that way there was a little bit of gap there, and there was basically airflow underneath those different layers of wood shake. So it's one of those things that as we think about roofs, that's how dynamic they are. It's not only just the desired affect for the thermal envelope, it's also the roof finish material that plays a role in determining whether or not we've made the right choices with the right assemblies, or if we have concerns that need to be worked out about that. Slope also plays a major factor in that, not only for the sake of shedding water and doing the fundamental job that a roof is supposed to, but also for making sure that we're applying the correct materials and sometimes even how that affects ventilation when it comes to sloped roofs or non-sloped roofs. The flatter a roof is, the harder it is for air to pass from a low to a high point. It also changes, for instance, some of the materials that are allowed, a lot of whom are a lot more sealing in nature. That's going to be things like your PVC roofs, your TPO, your EPDM. You have a number of different options there, but then it's also important to discuss that and right size that for what what implications is that going to have on the way that we plan this attack with our our design and our attic ventilation and what code sections are going to apply. We also, of course, have ventilation listed there. We have fire classification. That's one that I'm going to get into a bit later. But yes, as you build closer to another building, or as you build closer to a lot line, or if you're in a area like a wildland urban interface area, then definitely you're going to have a concern about what materials you're using on that roof to make sure that you're making that structure less prone to catching an ember during a wildfire event or from a neighboring property and seeing that then cause a conflagration on your home and spreading that fire. So there's an interest in definitely mitigating that holistically wherever possible. And then some of the other things that have come up for some consumers have been, desires for things like a walkable surface or deck. And so we see a lot of that in some of the infill projects that we see, replacements of like old Denver squares for more vertical construction, and they want that view up on like a master suite or something like that. And so that's changing the conversation about what's kind of in that consumer profile for your average residential home and seeing things like a walkable surface on there and what the plan of attack is with that. So roofing materials can vary dramatically. So I have a few pictures here of a number of basics, right? So we have tile roof on the left. In the center, we have asphalt shingles, and you can see that those have seen better days. I actually took that picture on an inspection where this person's roof on one side was getting replaced, and then on the other side, the insurance company decided not to replace the garage. And so that was just getting up there and taking a look and going, oh wow, this is rough. And then Cedar Shake, that one was taken from the Cedar Shake Bureau itself. You can see their little logo there in the bottom left. And yeah, beautiful job. Like, they can really look picturesque. And there's a number of things that aren't captured here in some of the stuff I have for you, thatched roofs and things like that. There's a number of alternative different styles and very old styles, green roofs, things like that. There's so many different ways to go about attacking this. But what I wanted to point out with this slide was really that there's no roofing system out there that's just out on its own without support. So almost every type of roofing material has some form of manufacturer's association that helps produce best practices for the industry. So if you're coming into this space where maybe you are looking more at roofs, or you're a building inspector that's getting trained up for the first time and trying to look at this relationship between energy code and what materials or what code sections apply to roofs, know that there's always a good manual out there for you from a manufacturer's designated association. A lot of them are referenced directly in the code, some are not. But it's important to know what resources you have out there. So I wanted to highlight that for everybody. Here we can see a couple of others, and feel free to put your comments in if you feel compelled. I thought that was a really creative installation on the left there. That's what's called a stone-coated steel roof. There's a number of manufacturers in this space, some of whom are even kind of local here to the Denver area, along with metal roofs. There's some manufacturers here in Colorado. And so we can see two different types of metal roofing there. And again, that changes some of the things about our fire classification. It changes things about how much ventilated space is going to be underneath that decking. It changes things about sort of the plan for airflow, and maybe some of the other materials and sort of the best way that a contractor wants to use towards properly installing that roof or not. And on the left, we can definitely see a concern on the left-hand side that is pretty rough, all things considered. So, all right, I will keep on rolling here. And here we see a number of other kinds of roofs. These are way more commercial in nature, but it's also important to remember that when we talk about residential roofs and the residential sections of the IECC, that can include multifamily, right? And so it's not without cause that you might have conversations about different roof types like this still aligning with those residential sections. So I think it's just a good pointer to keep in mind. On the left-hand side here, we see a chimney being penetrated through this roofing assembly, and we can see that they just tarred up that bottom edge of shingles in order to seal that in. And that's not the right way to do that, in case anybody was wondering. For those that might be uninitiated in that space, if you're raising an eyebrow saying that doesn't look good, you are correct. What you would want is typically counter flashing over that. You'd also see step flashing on the sides. In some jurisdictions, they will allow continuous flashing as well, and more recent generations of the code have gone back and forth on that issue a couple of times. You'd see head wall flashing, which is basically an L-shaped metal flashing that runs under the shingles here that are running basically perpendicular or parallel, excuse me, to the wall. So the leading edge of that shingle. Let me turn on the little laser pointer so it's just easy to see. That leading edge of that shingle would be running parallel to the wall structure over here. And so that's where you'd see head wall flashing and again, counter flashing. So there are right and wrong ways to definitely go about roofing in this, but it's also a consideration again to think about all the places where we're abutting either the thermal envelope or unique bits of dissimilar materials in our construction, where we have masonry and then we have what looks like wood siding over here based on this picture. But it's a good example of remembering that we still have to have continuity of the thermal envelope. We have to plan for these spaces effectively. And then, of course, we have to make sure that the roofing materials themselves are installed properly. So now let's get into the science of this. Let's talk about the physics that are involved, because that really is the basis for the decisions that we make in our thermal envelope. So I'm going to take everybody back to, sophomore, junior year of high school, right, where we're talking about basic physics. And what we're talking about here is thermodynamics, right? And one of the basic rules in nature and in physics is that heat naturally flows from warmer to cool areas. We can see that in the weather. We see high pressure areas pushing out low pressure areas. We see high temperature areas moving in, across the Front Range. You can literally see that on the map. Well, the same is also true for the forces that our houses have to fight. And so we have here on this diagram, we have conduction. We can see that what conduction is, right, is that is passing through materials that allow for conduction. That's why we talk about thermal conduction in terms of our thermal envelope. How much conduction can steel or wood actually provide to allow heat into a space and transmit it through the wall cavity or through the ceiling cavity? And here we can see if it's cold outside, right? We see snow, and I know this is kind of a grainy picture. It's kind of a little distorted from trying to blow it up on this. But we see snow on the convection side, or excuse me, on the conduction side. And so that heat is trying to pass through from the ground or through from inside the house, through the attic space, and into a space where those excited molecules get to calm down in a cooler environment. So heat is naturally transmitting itself over to that cooler area. We also see radiation. We have the hot summer day where radiation, solar radiation, is penetrating through the attic space and working its way down to the ground, where once again, it wants to go to ground, it wants to be cool. And then convection, we can see those currents of heat and cool within the building themselves, right? And so here again, we see snow on the outside, so we know that we're warming this house. Heating is involved, and now we're cycling through that air and moving it through the space to try and create It's trying to basically normalize in all spaces and in all places. And so, why do we do all this, right? What is the point of dealing with the science of this and trying to create a good thermal envelope? Well, the number one reason, right, and this sounds a little funny to relate back to your life safety components, but I will get there, I promise, is that it's about the promotion of improved comfort. And there's rationale behind that, right? There's really good rationale behind that. One thing that we do is then the building acts in the way that we originally designed it to be used in, right? That includes heat, humidity. We're not over humidifying the air. We're not adding additional heat that we don't need. And the systems that are designed to be efficient for that system, for that building, are going to be able to work as well in that environment when it's sealed off properly, right? So that's our sizing of our mechanical components through things like our manual J and D. It's the entire holistic look of how this building's going to operate as a system. But what it also does when inhabitants are comfortable in a building, it reduces energy consumption because they don't need extra heating or cooling. So in my old office, I can tell you I had a number of permit technicians that every year around October, November, when it would start to get cold outside, but in this big building, some of the HVAC was just not very well planned for these areas, wasn't zoned appropriately for these areas, you name it. Um, in these areas, I would see them every year bring out blankets and bring out desk-sized space heaters. And they would be daisy chaining them in right onto the rest of the power strips for, the rest of their office space, their scanner, their printer, and then their space heater. And, not only is it additional energy inefficiency, right? We're using electric resistance heating in those places for people to feel comfortable. It's also dangerous. When we see enough of those chained together, that's how we get building fires and things, right? That's how those things can happen. So being comfortable in a building literally does improve its own safety. And then it protects the health over the long time use of that building. So a durable and complete thermal envelope effectively maintains the airflow and lets us, with intention, control that environment and make sure that we're not getting debris in the wrong places, dust in the wrong places, moisture, mildew, buildup of any of these items that deficiently allow that building to work properly. And so how do we create that boundary effectively? Well, we use an air barrier, a vapor retarder, and insulation. Those are our typical components of that thermal envelope. And that's going to help us create continuity, control that intrusion of air, and do so for the lifetime of the building. And so we're going to talk about how insulation specifically and the air barriers as well really relate to this. There is some discussion of vapor retarder, but as we get specifically into that, vapor retarders are not quite as common on that ceiling use, except in very specific circumstances. And we'll kind of get into that a little bit further. So this relates back, I think, to some of the stuff I saw in the chat there a minute ago about how does a roof provide these improvements to efficiency? Well, we have a number of different parts that are included in a roof when we talk about choosing things like color or material related to emittance, reflectance, and albedo. Now, emittance is how much heat a particular material is going to actually take in versus emit off, basically radiate off. Reflectance is going to be exactly that. How reflective is it? We know that if we have something like a mirror and we stand in the sun, we can direct those solar rays away from the rest of anything else that you want to point it at. It's also true for things like windows, right? When we look at solar heat gain coefficient, that's one of the components that we're able to determine is how much of this solar radiation is getting reflected away from the building and therefore not absorbed into my system. And then albedo, especially, is one of those discussion points about color. And that's really, I mean, we're getting down to architectural, design or preference and consumer preference. But it's no surprise that a black roof, like a black TPO, EPDM roof, for instance, is going to absorb a lot more heat than a white PVC or TPO roof, right? That albedo or albasticity is going to be able to direct that away from the building and prevent it from being absorbed into the rest of the assembly. So the graphic on your left is meant to just kind of, almost in a cartoony fashion, sort of describe what is happening there from a roof structure, where we have a high albedo structure directing as much of that solar radiation away as it can, and then it's allowing the insulation to basically work less hard to provide less conduction through this. So they're all working together as a team as part of that. And that's why it kind of relates to those decisions, even so far as, consumer preference decisions. Like I like a black roof or a white roof or whatever else. So here we have the 21 IECC for your insulation values, and you're required to provide that R60 pretty much throughout Colorado. That's pretty common, right? If you're into your other climate zones, we can definitely discuss that or take a look. It drops to 49, for climate zone 3. But ultimately, we're looking at a lot of these spaces in Colorado where we're talking about that R60. And on the right, you just see a section view of what that might look like on your plan set where you might see that identified for the first time. If we jump to the 24, we see exactly what I was discussing earlier about that sort of crest in the increase of insulation values and roofs, and then as it is sort of diminished over time now, where they're realizing, hey, maybe that's not going to provide the level of insulation payback that we would like, and so that became a pretty important conversation in the development of the 24 and sort of creating these rollbacks that you see in insulation values. Now you're down to that 49 in a lot of places. So why does that matter? Why do we need to discuss, depicting the thermal envelope and right sizing the insulation, other than obviously getting the right R value in the right place? Well, a couple of reasons. So I have it here for you in the 21. We're talking about section R103.2.1 for depiction of the thermal envelope. R103.2 would also describe some of the information on the plans, talking about, hey, you got to have your R values in this. I have to know the insulation types, all of that good stuff. Basically, there were not many changes to that section between the 21 and the 24, but it was relocated. So I wanted to make you aware that it is in 105.2.1 and basically tells us, hey, well, this is where we need to place the insulation. Now, it really matters then when you think about it for a number of reasons, because we've already talked about right sizing or right approaching our relationship with our insulation and our roofing materials and the design of the roof, right? The pitch of the roof, if it's a walkable surface, right, that means it's going to be flat. How complex is this thermal envelope going to be? Do we have jogs in places where it's going to go up or down, right? These are all important things to have demonstrated to us on the plan so we can be effective in whether or not the approach is valid and code approved. But also, does it align with your compliance pathway, right? So if we're doing this totally prescriptively, I'm going to cover some of that prescriptive information. Those are the insulation values that we were talking about a minute ago, prescriptive insulation values. Now, if I want to use a different method, say for instance, a component performance method where I'm going to use a res check and trade some of that off, I might be able to decrease some of that insulation by beefing up insulation in some other places, like my walls or buying better windows. If I'm going with a simulated building performance approach where I am completely using a software to describe this, that means that my values won't match. And so what I'll need is plans that show that and reports that also verify that based on the parameters of whichever method I choose, whether that be simulated building performance or ERI. But I'll still need all of that information tied together in a way that shows me demonstrably that we've got everything in alignment and no one part of this isn't going to play nicely with the rest. So one of the things I wanted to highlight for you in 402.2.1, we have a continuation of sort of an exception that's available for the R value method, where if you take your insulation in the attic space or in the roof space and you completely fill the area, but you also take it across the top plate of the exterior wall, you can actually do a decrease by one insulation size from R49 to R38. If it was R38, you can go to R30, but it is one of those things to keep in mind. And once again, this is right size based on your compliance path method and demonstrating on your plan set that that can, with the framing members that you have, clear that top plate. So again, it's about making sure that we're getting all the information necessary on the plans. Here's another one that we want to take a look at here. So in this plan set, we have an R30, and we have an R30 basically shown in these two sections right here. We have the section view that shows an R20 insulation on the exterior. Now, what do you guys think of this? I know that you don't have microphones on, but I really want you to think, like, can you do this? Would this have to come from a component performance alternative method? Would this have to be like a res check that's substantiating this? How would I be able to put R30 in these places? And I'll highlight, the easy answer for you. There's a reason you have a green arrow and a red arrow on here. And I'll explain exactly why here as we move forward. All right. Sorry, I turned on my laser pointer and now it's not letting me. There we go. So in the ceilings without attics exception, again, we have sort of an identified method where this is expressly not allowed for the component performance alternative. So it's about right sizing with that compliance path here. So right there. But we are limited to a 500 square feet area or 200% of the ceiling, or excuse me, 20% of the ceiling insulated area, whichever is less. Reading is fundamental, right? Um, where we can do an R30 if the ceiling does not allow from a structural perspective. We don't have the depth to be able to do this. And so if we go back to that picture that we were just looking at, we can see exactly why a circumstance like this might exist in the code. This is a perfect answer for something like a little kitchen bump out or something like that, where we'd effectively be reframing the overall size and roof pitch of this roof. We might be going with deeper members or something like that to accommodate the insulation. And instead, we're given an opportunity to right size an area for a lesser insulation value, provided it meets this criteria of fitting an interstitial space, and only for a small amount. And the reason I have this highlighted here in red is to remind you that you might get a plan set like this, where this is correct, but this wouldn't be allowed to be carried through possibly for the rest of that, because that break is telling me this is going to continue in that direction for the remainder of the roof ceiling assembly. That would be of concern. So again, we have a place where depicting the thermal envelope really matters and can help us make sure that we're getting overall compliance. We also have knee walls and attic spaces. Now, knee walls were actually added as a definition. I've got that for you on the next slide. And here we have a plan view where we can really take a look at this knee wall situation in an attic space. I've heard, multiple people refer to this multiple ways of like, vertical insulation or an insulation dam to be installed, right? But what this is describing is that we want continuity of our thermal envelope through this vertical assembly and continued through this horizontal assembly. And so we're going to use the values of a vertical assembly here and do that by furring out off of the truss and creating a sort of wall situation where we're going to be able to air seal that appropriately and provide all of the right criteria to treat this like the insulation wall that it should be. And it's going to be in all 6 sides. Perimeters and seams are going to be connected in all of this. So really important to make sure that that's recognized, and it's a recent addition in the 24 code. So we get a couple of new code sections. If it's blue, it's new when you get to join me for a class. Um, and so we can see here that when we separate that unconditioned space and conditioned space, we're going to use those wood frame wall values for our attic knee walls. We can also see here it's identified as roof truss framing separation. And where the vertical roof truss framing member is used, we're going to separate that as well and comply with the same wood frame wall criteria. So it's really getting specific about we're going to carry that insulation through in an effective manner. So now we're going to move into attic ventilation, right? And some of the discussion associated with that. And so the first thing that we have to ask is, well, where does it come from? And in our case here, it comes in R806 of the IRC. So this is a place where we really have to dovetail the energy codes requirements for our insulation values and the way that we're going to go about insulating with the IRC's requirements for a number of different components here. So not just ventilation, we'll talk about some other stuff, using foam plastics in certain places. We need to make sure we're fire protecting those. But we need to know first and foremost that this has sort of, I won't say primacy, but it's coming out of the roof construction area of the IRC for its ventilation requirements. So always good to know the right place to look. And really, we have 2 paradigms of this. We have a vented attic, which has been really common for a long time. It's a very common way to build. It's very anticipatable, I would say. A lot of folks know how to work in an attic space like this. You can also have some of this area dedicated for things like storage. We've also seen instances for a while there where people were putting appliances in this space. Your attic becomes outside of the thermal envelope. So we can see that that green acts as our thermal envelope here. And then we see that break where it goes flat. And then our roof peak continues. That's letting us know, okay, that ventilation is going to be drawing in that outside air through this space over here. And we want continuity of our thermal envelope in this green space. That obviously, a situation like that can very much adversely affect HVAC equipment that's located in it. And we'll talk about that very briefly in this discussion, but it's definitely something to be aware of. And then one of the other things here is that it's difficult to access without disturbing the insulation. The reality is that every time you climb into that attic, you're going to maybe displace this, maybe compress some of the insulation as you try to move about the space. And so that brings into that question of durability again that we started with, and what the effects are going to be over the lifetime. Then we have unvented attics, and we can see that continuity where this is carried up and over and all the way back down, right? Now, there are certain methods for being able to do this, and they are specific to climate zone, and we'll talk about that a little bit. I did remove a couple of slides just in the interest of time today that cover basically a method that's used only in climate zone 0, 1, 2, and 3, because it's just not germane to Colorado. But I think it's also important to understand the science behind it because it's still about the same principles of making sure that we're not vapor locking the assembly or creating a dew point in the wrong place. But that being said, we don't have the same problems for HVAC equipment that are located in here. Some of this can also be used for habitability, right? Some of this becomes now new habitable space, and there's a definition of habitable attic in the IRC for a reason. And some of this will dovetail with it. This typically is going to cost more. It's also going to use more advanced materials, but there are significant benefits to it. It's also a technique that's not necessarily familiar for everyone. A lot of folks have been building houses with flat roof spaces and attics for a very long time. And so it's not something that necessarily everyone gets right the first time. It takes a little bit of practice, takes a little getting used to what's included in the code for it. So I promised you that it occurs in 806. Well, 806.1 basically tells us, hey, you got to provide ventilation. It's required for attic spaces and for enclosed rafters. We should be providing cross ventilation in that attic space to the best of our ability to make sure that we're not creating problems of mildew, right? And we're getting that airflow through that space. Now, to the credit of the question we got earlier, obviously this has not always worked out terribly well. And we've seen instances of moisture intrusion in some areas in Colorado. And it is one of those things that even the code itself has bounced back and forth on. So when I started inspecting I was on the 2009 code. And when you read that, it actually had an exemption for ventilation based on the deference to the code official for climactic reasons. So, kind of speaking in that same realm, it has gone back and forth on this. Ultimately, I think we've decided as a whole it does represent good science to provide this, and it is the right thing to do. But even the code has waffled on this a time or two about what's the most effective approach and what should be used because of some of those concerns, like moisture intrusion that have been brought up earlier. So let's talk about our vents, right? We got a lot of different styles of ventilation, a lot of different tactics to be able to use. And what you're looking at right now are all exhaust vents. You can see that for a number of reasons because this is up at the top of the roof. And we'll be able to get into that a little bit more with some diagrams I have. But a lot of folks see these and they think, well, that's all ventilation is. That's why they kind of lead off the charge here. Whirlybird vents, like the bottom left here, have been around for a very long time. You can see them all over in houses in the metro area. These slant deck vents have definitely become very, very common. Ridge vent also very, very common. And some of the things or concerns that occur with this is definitely wind resistance and uplift. You get a lot of roofers that shoot this in with their same roofing nails, and they really should, according to the manufacturer, be using 2.5 or 3 inch hand-driven nails to make sure they don't crack through the plastic assembly, and simultaneously that they're getting the penetration into the roof deck that they need, because a 1.25 inch or 1.5 inch roofing nail going through this 1.5 inch deep assembly means that there's almost no bite into the OSB below. And so, some of these things we have to keep in mind. And it's one of those other parts to this that's a good reminder that roofs are not a place that are just touched by builders at the front end of construction. They're going to be touched multiple times. And oftentimes during re-roof permits, a lot of ventilation is either added or the style is changed. And that can either adversely or, it can also help a roof. But that effect does happen sort of repeatedly over the lifetime of the building, and it's something that's more dynamic than just the original design typically. Here we have a number of inlet vents or intake vents, and so we can see these installed at the soffit level. We can also see these called trimline vents. I think that's a brand name, but there's a number of these under shingle vents that are meant to go up the roof space a little bit. So that way we don't have to penetrate at the fascia or at the soffit there, but we still get that inlet. And so we might be wondering, okay, how do we go about, why do we have sort of multiple methods? Why do we have all of these different styles out here? And why do we have both inlet and outlet? Well, What you're looking at right here is what's called a balanced system for ventilation. And so we see intake, we see that convection principle being used in the same way that we were talking about earlier as something that we fight when we talk about our thermal envelope. In this case, when we have a vented attic space or we have enclosed rafters that are getting vented, then we are using this space effectively to be able to take air in from the bottom and exhaust it through the top, which is going to hopefully have a cooling effect overall on this roof, help normalize some of that temperature, but also it's going to pass that air through to make sure that we're not sealing that in, creating a dew point. It's going to help move some moisture out of the space as well when done appropriately. So when we talk about minimum vent area, that's the first thing we go to is 806.2. Now, typically we use that 1 to 150 ratio in order to measure this. And this venting calculator over to the side here is based on a particular manufacturer. So I want to be clear, it's not code necessarily to always describe this. Some manufacturers have some very specific guidelines for installing their product. And you'll notice here this definition that says net free ventilating area. And that's an important one for right sizing these vents because the vents themselves have mesh or baffles in them that are going to decrease the overall amount of venting space in there. So if I cut a 10 by 10 hole, you would think that would be 100 square inches. But the reality is that baffling and the grates and anything else that's in that vent assembly to prevent moisture from coming in or embers, which we'll get to later, a number of other things, that is also going to decrease that net free ventilation area. And so the manufacturers will tell you exactly how much in terms of venting you're going to get out of that product. So here we have a very, very plain, simple roof just for simple math. Right, at 1,000 square feet, we have this 1 to 150 ratio. We get 6.6 feet times 144 square inches. We get to say, okay, that's 950 square inches. So I need 950 square inches of net free ventilation area. And so it's really important to note that a 950 square inch vent is obviously going to have something covering it and decreasing the amount of airflow to it. So it's not going to be one vent, it's going to be many. And, that might be a mix of different ventilation. But right now, that's that 1 to 150 that we're looking at. Now, specifically, that's meant to be exhaust ventilation. So in a circumstance like this, where we might have more mix and vent clearance here, here we're looking at an instance where we're going to be doing some intake at the bottom and we're going to have baffles. The baffles themselves need to have a 1 inch clear space to be able to be maintained and to get that flow of air up through that process. The baffles are also required to be installed at all of the bays, not just some or not just some with intermittent venting, but all of the bays because air is going to disperse and diffuse into that cavity. And so basically code has decided, yeah, that makes more sense. We're going to make sure that that's continued up the process. Now here's that same calculation under balanced ventilation, where we do 1,000 square feet of roof, but now we get to use a 1 to 300 ratio that we see in 806.2. And that lets us delineate 50% exhaust, 50% intake, and split that up. And now that 950 inches is closer to 480 inches on each side here, right? Or excuse me, that's the 1 to 300 method. So that makes us be able to give that as the total. And now we get to parse that out high and low at 50%. So that's 240 and 240. That's how much more effective a ventilated, balanced ventilated system is it's almost doubly so. So here's really what's happening there when we talk about this. We see that soffit ventilation come through, we get airflow through the attic, and then passing through out through our vents. We have slant back vents over here. We have ridge vent, right? Now, some of these are not meant to work in concert with each other, and that's an important thing to note. A lot of manufacturers will tell you, pick one and stick with it because we can create instances of short cycling and create even intakes in the wrong places. Going back to that question we had earlier about getting some airflow in there and then getting some moisture buildup as well. So we definitely want to see more in the minimum of 40%, but not more than 50% of ventilation in the upper portion of the attic. Right. So we basically found it used to be that 50-50 split. Sometimes people would put a little more in the top thinking, oh, I got to vent it out. I got to get it out. And the reality is no, that can create that short circuit issue that I actually think I have in another slide here just coming up. So right here, too much exhaust, right? This will create that short circuit sort of issue where now, because these, say, whirlybird vents are now the highest point to this peak, you can see that what's happening is that these slant back vents are actually becoming intakes and trying to take in air and then exhaust it through the space, diminishing any of the ventilation installed down here. That can definitely create that circumstance where we're getting moisture intrusion in the wrong places, like that question brought up from earlier. So, yeah, too much intake will become part of the exhaust system. Industry says it isn't a problem like too much exhaust. So, can you do too much intake? Yeah, technically. Air will go to that space wherever there's low pressure to try and get out. But basically, the take is that it's less of a concern than putting in too much exhaust, which was often super common and sometimes prescribed by roofers on re-roof projects and the like. And then we get over to unvented and enclosed attic spaces. And now this is where we get the permission basically out of the construction in the IRC to say, okay, we can do a fully spray foam cold roof or hot roof. I've heard it referred to both ways depending on where I'm at in the country. Where we can fully insulate that space. We can use air impermeable insulation. All of those things are on the table, but we get some specific conditions. And I know we're getting close in the hour here, so I'm going to move through them quickly, but feel free to raise any questions that you have. So first condition is that the unvented space is completely within the building thermal envelope. So we see that full continuity included in that area. This is our insulation, air barriers, air sealing, glazing, right? All of those components that we talked about earlier when we talked about creating the thermal envelope are included when we discuss that. So if we have anything that's not really following that line, then we have to take a deeper look at it to say, is this all enclosed within the thermal envelope? Here's a good example of a plan set that you might get where you see spray foam insulation going over our truss systems here. And so we see that continuity all the way around the thermal envelope to be able to provide that, right? That's that pink or that purple, depending on if you're a little colorblind like I am. Condition 2, you can't use a class 1 vapor retarder on the unvented side of the attic assembly. So this cannot happen in this space, right? Polyethylene sheeting, things like that. And remember your classifications of air barrier, or excuse me, of vapor retarder, you have 3. And this is just discounting the least permeable of them. This still allows for a class 3 or a class 2, like craft facing, things like that. So remember, polyethylene, perforated aluminum foil, those are your class 1s. Class 2 is craft facing. Class 3 is latex paint, for instance. Remember how we talked about wood shingles needing some ventilated airspace here? We definitely see a different tack on that. And again, this goes back to a change where our finished roof product actually influences the way that we're able to insulate this properly. And as you can imagine, you can build this with the correct insulation, and then because of a hailstorm, you might be stripping off the roofs, and somebody says, "Ooh, I'd love a wood shake roof like my neighbor." And this is a place as a code official and as a an installer or a builder that you want to be really, really specific on to know the code and to know what the parameters are where you might not be able to provide that service because these roofs actually do need that breathing capacity that might be eliminated from them based on certain insulation criteria if they don't have some sort of gap or substrate in there that's going to allow for a little bit of a cavity for airflow. So here we see what's used is called a ventilation mat. It's a specific product meeting that criteria to add that 1/4 inch of vented insulation. And then in climate zones 5, 6, 7, and 8, any air permeable insulation shall be a class 2 vapor retarder or have a class 2 vapor retarder coating and direct contact. So we see that basically specifically identified here in the attic space and using that craft face insulation here. And now where we're using air permeable, we're going to seal to the perimeter here to form that continuous layer. And now we get into air permeability specifically for the insulation types being used and how much of it. And so we get a breakdown in 5.1, 5.12, 5.13, 5.14. So where only air impermeable insulation is used, right? So this can be complete spray foam, rigid foam, things like that, right? It's going to be directly applied to the underside of the structural roof deck. And then where we use air permeable insulation, it shall be directly applied below the structural sheathing, rigid board, or sheet insulation directly above. And we have to use this table 806.5 for condensation control. That means that we're effectively using this in order to be able to make sure that we're creating that dew point separate from the rest of the insulation that might be used in the cavity. We're making sure that we're getting that moisture out in the right places. And here we have a mixed system of spray foam insulation, and then sometimes the spray foam insulation is really the total insulation needed. We also may need a ignition barrier in order to protect that insulation. For that, we go to Chapter 3 of your IRC. So that way we can look at specifically the requirements associated with those foam plastics. Again, we look at that condensation control related issue. And then alternatively, we can also do exterior insulation in this case, right? So this is below the substrate, but above the roof deck here where we are getting that full amount of insulation. And then in here, we see that air control layer being identified as part of this assembly. And you see that there's a calculation purpose here for dew point, and we want to make sure that we're observing and following. And then in 806.5, we see identified here are specifics for our different insulation values. I really want to highlight the footnotes here for you that these contributions to contributes, but does not supersede the requirements of 1102, right? Which is going to be, if you're just in the IECC, that's going to be equivalent to 402 for your insulation values. But we're basically letting you know there that, hey, this is you can count this as part of the total insulation you need for that assembly, but this does not supersede. You don't say, well, I only need an R30 now because that's what this tells me. It's saying that this particular material to act in the way that it needs to for condensation control must be of this thickness or greater. And now we're going to jump over to ducts located in some of these conditioned spaces. Once again, we already talked about that line in the thermal envelope and the depiction of it. Obviously, to meet some of the criteria, if you're in the 21 and you're getting that additional efficiency package of keeping everything in, then that's an easy one to shoot for. If you can prove manual D shows it's all inside, and then your depiction of the thermal envelope shows it all inside, then you're in great shape. As you get into more complex ones, like in 24, where you might have multiple different credits that you're going for, and trying to get credit for one of them might be something like this. And so when you have your ceilings, if you have a flat ceiling, it is important to remember you need that R19 minimum below if you need to bury this duct where you're going to be able to get that insulation in. So that might mean furring down. It's also important to note that this R19 is judged independent of the insulation used for that duct itself. And we're going to make a continuity of air barrier to separate that from our unconditioned space. And then as we bury ducts here, we can see that if we have exposure, we're going to that R8 for our supply and return ducting. We're doing R19 minimum total over this. So on some of these, we might have to have a break where we're furring down or we're bringing down that insulation in some way or another, but we're getting that full amount of insulation around this. Regardless, R38, R49, we're still getting that continuity around our ductwork because the leaks are just that important. It's that much of an energy savings to keep all of your ductwork within that thermal envelope where possible. And now we're on to some Colorado specific considerations for you. So like I told you guys, the Wildland Urban Interface Code is definitely here for a lot of jurisdictions in Colorado. And I don't want to complicate things too much, but I do want to bring to your attention that it's worth pointing out or worth paying attention to that this might change some of your approach to things like your ventilation, choices of roof style, things like that. And so one of the things that comes up oftentimes is description of non-combustible in a lot of these. And so one of the things that I wanted to identify for you, and this is right out of the Wildland Urban Interface Code, is these sections for 504.2, 505.2, and 506.2. Now, if you haven't read that code, I will give you the quick and dirty of it. In 504, you're talking about the most ignition prone. Then 502 is the second or moderate tier, and then 506 is the least tier. So you're going to see that kind of happen a lot, where the more stringent requirements are going to be associated with these two, and the lesser ones are going to be associated with this one. That's just a very high level kind of brief thing. But you have to have a Class A roof assembly. And it's important to remember that it's a Class A roof, in its totality here versus a Class B roof, right? And so there are many metal roofs, for instance, that are considered Class B because they're going to transduce that heat, right? Transmit that heat right into their framing members because of thermal conductance. So my example here of a bunch of, chilies when I'm making, this was literally me making salsa last week. But browning these, right, frying them up in the pan a little bit, getting a little bit of color is a perfect example of that heat transmitting through into the rest of the assembly. So it's important to keep that in mind that even if something seems like it's non-combustible on the outlook, you may need to take a deeper look at it, and from there, even the finish might impact the way that you approach your ventilation or your roof insulation. There was a manual put out some time ago. This is based on the 2009 International Wildland Urban Interface Code. But what you see here, and the reason I wanted to bring it up, is that there are multiple methods for being able to install that ventilation. And some of these came out of the Colorado State Forest Service through this particular document, where they were moving around the location of some of these vents to things like the face of the fascia, or out away from the tightest part here to the wall assembly. And you can see when you have intakes here that their concern is that hot gases from a fire are going to abut the house, and then this creates a little envelope for them to cycle in and then intrude into the rest of the space. And so we're going to see how that actually changes performance requirements for vents. So we've got kind of two different parts to this here. Here we see that trim line vent we were talking about earlier. But we get new requirements in the 24 version of this code, some of which are required just specifically for testing. So this is this ASTM E2886, where it's basically saying, hey, we have to make sure that these products are tested to this. And that's fine. That's an easy one, I guess, in terms of just determining, hey, is your product compliant or not? But this is what I really wanted to highlight with you, is that this limits the size of vents in a number of different places. This is including foundation vents, attic vents, crawl space vents. A number of different types of vents are limited in their ability to be a certain size and also have to be equipped with a non-combustible mesh product. Now that is definitely also going to affect that ventilation component. So when we talk about the overall ability to be able to navigate, how do I insulate my roof? How do I ventilate it properly? And how do I treat that whole residential assembly properly? This is also going to have an impact that might change some of the products on the market, some of the availability for products on the market, and some of the choices to be made in the field. And that is my presentation, guys. I think we've got a couple of minutes if anyone has questions or wants to get into anything specific.
Awesome. Thanks, Andre. Okay, so if you have a question, go ahead and write in the chat or the Q&A, or if you'd like to raise your hand, you can also do that. Looks like we do have a few questions in the chat for you, Andre. So the first one that I've got for you is the outer edge. Sorry, it's jumping around on me. The outer edge of a top plate usually receives directly over it, blocking between trusses or rafters, flush with the exterior face of the top plate. Would we be meeting code if we only take R30 to the inside face of the blocking over that top plate?
That's a great question, Jesus. And my first inclination, because I've seen this done in a few places, right? One of the other interesting places about this is in the IRC, back in, I think it's the 2015 version, we added the ability to do the sacrificial soffit option, right? So you used to have to do, when you were within 5 feet of a property line, you used to have to do like your 2 layers of 5/8 type X and block all the, take care of that. Or you could block off the soffit completely. And the way I read this, the way that that is expressed in the energy code is it wants clear span over that. So any pinching or any stopping of that prior to clearing the entire width of the top plate appears to me that it would be considered to then no longer meet the criteria for that exception. I know that probably feels like splitting hairs. So I know there are a couple of really good building scientists that have done like FLIR camera looks at some of that to see how much of a difference compressing that insulation at that place makes. So it might be worth doing some additional research on that topic, but my first intuition from what I've heard from other folks and reading that is it does need to clear it, even though it does then get in conflict with some of the other either typical practices or even other options in the code that we would like to take for sometimes life safety purposes. So yeah, it's a great question.
Thanks, Andre. Okay, next one up is the USDE told me in the 1990s that they would never require anyone to install more than R38 in the attics on a horizontal ceiling. They said that adding any more depth would not offer any payback. Is this proving to be true?
I think the calculation there is, there's something to be said about that. There's a point at which, an R90 can perform significantly better than an R1000, right? At a certain point, there's a diminishing marginal return. And so I think you're right, Derek. I think that, R38 used to be the line for dimensional lumber, right? That was really the careful line to be considered there. We've already kind of gone past that to a degree, to a place now where we're looking at more of a we're basically prescribing, healed trusses. And that is, for some folks, that's a frustration, right? The IRC was always meant to be a document where you could build your own home, and do so without the help of a design professional and still do so safely and prescriptively. And then we've hit a point where the energy code actually would require you to have a structural member designed by an energy or by a design professional specifically to accommodate an energy requirement. So there's a lot of folks that look at that, I think, with the same sort of concern, especially folks with your experience that have been in the game as long as you have. So I'm inclined to agree, but yeah, that's I think there's a lot of folks involved in that debate.
Thanks, Andre. Okay, next one is if you could touch on cold roofs when they are appropriate and effective.
Yeah, yeah. So from a climate perspective, I mean, here's the deal, is that the number one thing that I think you get out of cold roofs is the ability to keep everything within the thermal envelope and to use that space for your HVAC. Right now, I've heard from a number of folks in different climate zones with some of the difficulties associated with making sure that they aren't creating those artificial dew points. And if you have significant concern, because Brian, I don't know where you're at in the state or, like what climate zone you're in specifically. So if you want to catch me offline, please take my email address now and we can get into a bigger discussion on this. But they're proving now that we're getting better information about how to layer this insulation properly and to make sure that we're creating dew point in the right place and, design professionals providing dew point calculations. We're getting to a place now where I think we can say it's a bit safer to be able to do without creating some of like the moisture intrusion problems that there used to be. But I'd be happy to connect with you because I feel like that's a long answer, and I think I'm getting pretty close to out of time.
All right, that brings us to the end, Andre. Thank you again for your great presentation today. And if folks have any questions, feel free to email Andre or submit a question to the helpline, and I will go ahead and assign it to Andre as well. So you got multiple options there. All right.